Hi everyone. In this class, we are going to discuss about solutions of Maxwell's equations. Solutions of Maxwell's equations in uniform plane wave. So the simplest wave solution of Maxwell's field equations are uniform plane wave, which are characterized by uniform field over infinite plane surfaces at fixed instants. In other words, if the phase is same for all points on the plane surface, if the phase is same for all points on the plane surface, it is called plane wave. And if the amplitude is also constant over the plane surface, it is called as uniform plane wave. So that is the definition of plane wave and uniform plane wave. What is the plane wave? If the phase is same for all points on the plane surface, it is called as a plane wave. And if the amplitude is also constant over the plane surface, is called as uniform plane wave. For uniform plane wave, we have seen that the only components are present and the rest two components are zero. Thus, uniform plane wave is a special case of electromagnetic wave. Uniform plane wave is a good application or special case of electromagnetic wave. So what is the condition of the uniform plane wave? So let us now we can determine the solution of Maxwell's equations in electric field intensity and magnetic field intensity. That electric field intensity and magnetic field intensity is propagating in the z direction, then dou E bar by dou x is equal to 0 and dou E bar by dou y is equal to 0 in case of electric field intensity. So whereas in magnetic field intensity, the components dou E bar by dou x is equal to 0 and dou E bar by dou y is equal to 0. Along the direction of the propagation, the derivatives, that is dou by dou x is equal to 0 and dou by dou y is equal to 0 if the electric fields and magnetic fields are propagating along the direction of the propagation. And further, since the wave is propagating in the z direction, so it will have the components. It will present Ex and Ey components and there is no Ez components. So that is the condition of the uniform plane wave. Uniform plane wave. If the wave is propagating along the direction of the propagation, the uniform plane wave conditions are dou by dou x is equal to 0, dou by dou y is equal to 0, and there is no field components, that is electric field components and magnetic field components 0 along the direction of the propagation. That is the condition of uniform plane wave. So we know that the homogeneous wave equations for the free space electromagnetic wave equations are derived in previous classes. So that are del square E bar is equal mu naught epsilon naught dou square E bar by dou t square. So this is the electromagnetic wave equation for free space of electric field intensity. In this equation, del is the vector differential operator. So what is the vector differential operator del expression? Del is equal dou by dou x ax bar plus dou by dou y ay bar plus dou by dou z az bar. So what is the LHS term of the electromagnetic wave equation of free space? Del square. So del square means del dot del. Del dot del is del square. So del square is written as del dot del. What is the del? Dou by dou x ax bar plus dou by dou y ay bar plus dou by dou z az bar dot another del. What is the del? Dou by dou x ax bar plus dou by dou y ay bar plus dou by dou z az bar. But we know that according to the concept of vector analysis, the dot product of same unit vectors are unity and the dot product of different unit vectors are 0. That is, ax bar dot ax bar is equal to 1, ay bar dot ay bar is equal to 1, az bar dot az bar is equal to 1. And dot product of the different unit vectors. That means ax bar dot ay bar is 0, ay bar dot az bar is 0, az bar dot ax bar is 0. So, therefore, del square value is dou square by dou x square plus dou square by dou y square plus dou square by dou z square. So, we know that the vector form of the electric field intensity is Ex ax bar plus Ey ay bar plus Ez az bar, where Ex, Ey and Ez are the components or amplitudes along x direction, y direction and z direction. And ax bar, ay bar and az bar are the unit vectors in x, y and z direction. So that is the vector form of the electric field intensity. Substitute del square value and the vector form of the electric field intensity expression into free space of the electromagnetic wave equations. So we get del square is dou square by dou x square plus dou square by dou y square plus dou square by dou z square into E bar. Vector form of the electric field intensity is Ex Ax bar plus Ey Ay bar plus Ez Az bar is equal mu naught epsilon naught into dou square by dou t square into E bar. So E bar is the vector form of the electric field intensity. So LHS side multiplying all the terms and similarly on RHS side also multiplying on the terms. After that, comparing on both sides Ax bar components, Ay bar component, Az bar component. So compare both sides Ax bar components. We have dou square Ex by dou x square plus dou square Ey by dou y square plus dou square Ex by dou z square is equal mu naught epsilon naught dou square Ex by dou t square. So comparing on both sides Ax bar component, we have the resultant expression. So similarly, comparing on both sides Ay bar component, we have dou square Ay by dou x square plus dou square Ey by dou y square plus dou square Ey by dou z square is equal mu naught epsilon naught dou square Ey by dou t square. And comparing both sides Az bar component, we have dou square Ez by dou x square plus dou square Ey by dou y square plus dou square Ey by dou square Ez by dou z square is equal mu naught epsilon naught dou square Ez by dou t square. The electric field intensity is propagating in the z direction. So for uniform plane wave is propagating in the z direction, electric field intensity is propagating in the z direction. The conditions are dou Ex by dou x is equal to 0 and dou E by dou y is equal to 0. And there is no field component along the direction of the component. That is Ez field component is 0. And the second derivative is also 0. Dou Ex by dou x is equal to 0 means that is the first derivative. And the second derivative is also 0. That is dou square Ex by dou x square and dou square Ey by dou z square, dou y square is also 0. So applying uniform plane wave condition in the above equations, above three equations. So we have dou square Ex by dou z square is equal. So applying these conditions into in this equation, above three equations mean this equation and this equation and this equation. Okay, applying these conditions into above three equations, we have dou square Ez by dou square Ex by dou square Ex by dou z square is equal mu naught epsilon naught dou square Ex by dou t square. And second equation, dou square Ey by dou z square is equal mu naught epsilon naught dou square Ey by dou z square. And from the third equation, the third equation, the field component Ez is equal to 0. So because of that, in third expression, there is no expression. From the third expression, there is no resultant expression. So from equation, that is, so this is equation 1 and this is equation 2. So similarly in magnetic case also, magnetic field intensity. If the magnetic field intensity is propagating along the direction of the propagation, similarly dou square Hx by dou z square is equal mu naught epsilon naught dou square Hx by dou t square and dou square Hy by dou z square is equal mu naught epsilon naught dou square Hy by dou t square. Similarly, with the magnetic field intensity, H bar is propagating in the direction in z direction. After applying the uniform plane wave conditions, we get resultant expressions. So from the above equations, Ex, Ey, Hx, Hy are magnitudes of electric field intensity and magnetic field intensities. So the above equations are the wave equations that are the differential form of second order. The above equations are the wave equations. That wave equations are the second order differential equations. So the general solutions of the above equations. What are the above equations? Four expressions. If the electric field intensity is propagating in z direction, we get two expression, and the magnetic field intensity is propagating in the z direction, we get another two expression. So totally four expressions. That four expressions are the second order differential equation. The general solutions of that equation is given by E bar is equal to F1 of z minus Ct plus F2 of z plus Ct. Similarly, in magnetic case also, H is equal to F1 of z minus Ct plus F2 of z plus Ct. That is the general solution of above equations. In this equation, the first term F1 of z minus Ct and F2 of z plus Ct is the functions. F1 and F2 are the functions of z minus Ct and z plus Ct. In this equation, the first term F1 of z minus Ct indicates if the wave is traveling in positive z direction. Wave is traveling in positive z direction. And the second term indicates, what is the second term? F2 of z plus Ct. Second term indicates wave is traveling in negative z direction. A wave is traveling in negative z direction. First term indicates wave is traveling in positive z direction or forward direction. Second term represents if the wave is traveling in negative z direction or backward direction. So from the above equation, where c is the wave velocity, c or v is the wave velocity. In free space, what is the wave velocity? V or c is equal to 1 by square root of mu naught into epsilon r. So what is that value? Velocity of the free space 3 into 10 to the power of 8 meters per second. Okay. The general solution of the wave equation consists of there are two terms. And the first term indicates wave is traveling in the positive z direction, and the second term represents wave is traveling in negative z direction, forward wave and backward wave. However, there is no reflecting surfaces. So that the reflected wave travels back to the source. The second term of the equation 2 becomes 0. The second term of the above equation means general solution expression of the second term will be 0. So we have the remaining expression E is equal to F1 of z minus Ct, F1 of z minus Ct or F1 of z minus Ct, where C or V is the wave velocity. So what is the wave velocity? C or V is equal to 1 by square root of mu epsilon. And beta is the phase shift constant. What is the phase shift constant beta? 2 pi by lambda. Okay, the general solution of the wave equation may be represented in the form like trigonometric form or exponential form. The general solution of the wave equation may be represented in the form like trigonometric form or exponential form. So what is the trigonometric form of the general solution? So the trigonometric form of the general solution is Ex is equal to sine beta of z minus Ct plus sine beta of z plus Ct. Okay. First term represents wave is traveling in positive z direction, and the second term indicates wave is traveling in negative z direction or backward direction. So multiplying beta with within the bracket term, sine of beta z minus omega t plus sine of beta z plus omega t. Sine of multiplying beta, sine of beta z minus beta ct, sine of beta z plus beta ct. Beta c is equal to omega. What is the beta? The beta is the phase shift constant. What is the phase shift constant beta? 2 pi by lambda, where c is the velocity. So what is the velocity? F into lambda. F into lambda. So substitute beta value and C value, we get beta C is equal to omega. So because of that, this equation Ex is equal sin beta z minus beta Ct plus sin beta z plus beta Ct is also written as, also represented as Ex is equal sin of beta z minus omega t plus sin of beta z plus omega t. Similarly, the general solution and another wave equation, the general solution Ey is equal sin of beta z minus omega t plus sin of beta z plus omega t. There are four expressions from the electromagnetic wave equations of the free space. We get four expressions after applying the uniform plane wave conditions. And equation 1, general solution Ex, that is sin of beta z minus omega t plus sin of beta z plus omega t. And the second expression, similarly, the second expression of the general solution is Ey is equal sin of beta z minus omega t plus sin of beta z plus omega t. Similarly, third expression general solution and fourth expression general solution. So the general solution of the wave equation may be represented in the form of trigonometric form or exponential form. So this is the trigonometric form of the general solution. So from the above two expressions, the solution may be either a single term or both the terms. Single term is if the wave is traveling only in positive direction, positive z direction. So both the terms mean positive direction and negative z direction, positive z direction and negative z direction. Okay, that equations 1 and equation 2 already calculated. What is equation 1? Dou square Ex by dou z square is equal mu naught epsilon naught dou square Ex by dou t square, that is equation 1. And equation 2 is dou square Ey by dou z square is equal mu naught epsilon naught dou square Ey by dou t square, that is second equation. These two are the wave equations of electromagnetic wave equations for free space. So writing the above two expressions, above two equations, sinusoidal time varying fields. Sinusoidal time varying field. So the sinusoid of the time varying field can be determined. The derivative factor is simply represented by j omega. The derivative factor dou by dou t is simply written as or represented as j omega. Now here the RHS side dou square by dou t square. So dou by dou t is simply represented j omega. Dou square by dou t square is j omega whole square. So therefore, from this equation or this equation, whatever, any one equation, consider any one equation. So dou square Ey by dou z square is equal mu naught epsilon naught j omega whole square into Ey. So that is equal j square value is minus 1, a square value is minus 1. Therefore, dou square Ey by dou z square is equal minus omega square mu naught epsilon naught into Ey. So RHS term is coming to the LHS side. We have dou square Ey by dou z square plus omega square mu naught epsilon naught Ey is equal to 0. So this is the standard second order differential equation. The general solution of this equation is given by in exponential form. The general solution of the wave equation may be represented in trigonometric form or exponential form. The trigonometric form already discussed. So now we are going to discuss about exponential form of the general solution. So the above equation is the second order differential equation. That second order differential equation general solution is Ey is equal a into e power minus j beta z plus b into e power j beta z, where beta is the phase shift constant. The phase shift constant beta is equal to omega into square root of mu epsilon. Beta is omega into square root of mu epsilon. So that is mu square root of mu epsilon. Now here this is the second order characteristic equation. This equation is represented by Dou square Ey plus omega square mu naught epsilon naught Ey is equal to 0. How to calculate the roots of the second order equation? Minus b plus or minus square root of b square minus 4ac by 2a. So using that expression, we can find out the value, that beta value, that roots are omega into square root of mu epsilon. Omega into square root of mu naught epsilon naught or mu epsilon. In free space, mu is equal to mu naught, epsilon is equal to epsilon naught. Where v is the wave velocity, the wave velocity v is equal to omega by beta, and phase shift constant beta is equal to 2 pi by lambda. So for time varying notation, the above equation may be represented, may be written in time varying notation, that above equation into e power j omega t. Therefore, Ey is equal a e power minus j beta z plus b e power j beta z into e power j omega t. Multiplying e power j omega t within the bracket term, we have a into e power minus j beta z into e power j omega t plus b into e power j beta z e power j omega t. So these two exponential terms is written as e power j of omega t minus beta z, and these two exponential terms is written as e power j of omega t minus beta z. So we have the component Ey is equal a into e power j of omega t minus beta z plus b into e power j omega of e power j of omega t plus beta z. Okay, so this equation indicates there are two waves. One is the forward traveling wave and another one is second backward traveling wave. The first term represents the wave is traveling in positive z direction, and the second term indicates wave is traveling in negative z direction. Okay, similarly in terms of cosine terms, previous already discussed in trigonometric form, sinusoidal terms, a cos of omega t, a sin of omega t minus beta z plus b sin of omega t plus beta z, where a and b are the arbitrary complex constant. Similarly in cosine forms, general solution Ey is equal a cos of omega t minus beta z plus b cos of omega t plus beta z, where a and b are the arbitrary constants. The first term represents wave is traveling in positive z direction, and the second term represents wave is traveling in negative z direction. Okay, so this is the concept of solution of Maxwell's equations in uniform plane. Solutions of Maxwell's equation in uniform plane. What is the solution? In trigonometric form or complex exponential form. In trigonometric form, what is the solution? Ex or Ey is equal a into sine of omega t minus beta z plus b sine of omega t plus beta z in terms of sign notation. And another form of the trigonometric form of the solution is a cos of omega t minus beta z plus b cos of omega t plus beta z. And that is the trigonometric form general solution. And in exponential form general solution is Ex or Ey is equal e power minus j beta z plus a, capital A into e power minus j beta z plus capital B into e power j beta z. So from the above general solution, the general solutions, capital A and capital B are the arbitrary complex constants. So from the above expression, the general solutions, the first term means sine of omega t minus beta z, cos of omega t minus beta z, and e power minus j beta z is the wave traveling in positive z direction. Wave is traveling in positive direction. And the second term means sine of beta z plus omega t or cos of beta z plus omega t e power j beta z represents the wave is traveling in backward direction. Backward direction means there is negative z direction. So this is the concept of solution of solution of Maxwell's equations in uniform plane view. Thank you.